Right, so we're going to talk about the normal distribution. It comes up fairly frequently, and it's very similar to our binomial distribution in a lot of ways. We're talking about a lot of the same terms as far as variance and standard deviation of mean or expected value. We're using normal distributions for continuous data. Just a reminder about what continuous data might be. Scores on an exam, are they continuous?
No.
What about the time it takes to run the 100 metres? Continuous, that is continuous because you can have any value for that. Another example is height, which is what we're going to look at for our example here, over the side. Now, the things that we need to know when we're dealing with normal distributions, it's really important that we have our mean and our standard deviation. They make a heap of sense when we're talking about the normal distribution. The other characteristics of a normal distribution is it must be symmetrical around our mean value. So we must have one bell-shaped top. Okay, so does anyone know what we call this? It's got a special name. A bell curve. And it's been used for a very, very long time. It's very useful because it helps us determine the significance or the rarity of an event occurring. So to give you some perspective about how the old system used to work, we used to all perform in our subjects, we'd get a score, and that would be multiplied by our school score on the QCS. They'd get everyone's scores of the state and put it on a big distribution like this, and then you would get an ATAR base or an OP based on your score. If you were in the top 1%, for example, you were 3 standard deviations above the mean, you got an OP of 1, and then you work your way down. On the other end, it was the same. To get an OP of 25, you needed to be on the bottom 1 percentile. Cool? That's how we used to use it, which is, in some regards, it's still used, but we use it to determine how significant an event is. So if I was to think about this distribution here, where I've got my height versus my frequency, this could be the average height of Year 12 students over the years, or the height of Year 12 students at St. Pat's. Or Year 12s across Mackay. Let's just call it across Mackay, right? What does that tell you about what's the average or the mean height of a Year 12 student? 170 centimetres. So what the normal distribution does is it allows us to determine, well, how significant is my height and what's considered, what percent of the population falls within a certain range. So let's say the standard deviation of this graph, of this distribution, is 5 centimetres. I would have a standard deviation, that would represent 1 standard deviation above and 1 standard deviation below the mean. So between 165 and 175 centimetres, I would expect to find 68% of my population. Does that make sense?
I'm just making up that percentage number.
No? No?
No, 68.
Because that's what normal distributions do. So within 1 standard deviation, because of the way the bell curve forms, between 1 standard deviation of a mean, we have approximately 68%. Now we have to have lots and lots of samples for that to work.
Oh, okay.
Cool?
So you just always go 1 standard deviation,
Yep.
so that's 68%.
Yeah, if you're 1 standard deviation either side, within 1 standard deviation of the mean, then you are within the 68, middle 68 percentile. So if I saw a student that was 165 centimetres, they're a little bit shorter than normal, they're not abnormally short, if that makes sense. Cool? If you feel attacked by this, that's on you. Now, I've used this example for many years and there's always kids that feel attacked, I don't know why. Now, between 2 standard deviations, which would be 10 centimetres either side, I hold 95% of my population. So So 95% of my population is held within 2 standard deviations of 1 mean. So that means when I was, buying uniforms or ordering uniforms at the start of the year at St Pat's, and I was trying to organise for kids that were between 175 and 180, I could get an idea about how many large uniforms I'd need to order. That would represent 2.5% of the population in the top end of the category. So kids bigger than 180, I'd need to prepare for 2.5% of the population. So 2.5% multiplied by, say, 200 kids, multiplied by 3 uniforms. The uniform shop would know they only need to provide about 10 of those uniforms, rather than booking 300 of them, waiting for the kids to rock up. Sweet? Does that make sense? The third standard deviation holds 99.7%. So that's pretty much our entire population is held within 3 standard deviations of our mean. Does that make a bit more sense or not?
Absolutely.
Absolutely. So,
Thank you.
I want you to compare these 2 graphs, same variables. I'm still dealing with height, but in the situation, I should do it on the same graph so it makes more sense, but I've done some drawing on that graph. I'll do it on the same graph. Which one has a higher standard deviation? A larger standard deviation. Hopefully this works. Has everyone got that image down before I destroy it?
Yeah.
Okay, good. Is that a normal distribution? Does it have a bell curve? Is it symmetrical around a mean? So it's still a bell curve. What's different about it? Lower and wider. So remember, what standard deviation a measure of? Standard deviation? Spread. It's a measure of spread. So does my attempted black marker have a larger standard deviation, or does my blue one? The black one has a larger standard deviation, which can be a little bit counterintuitive, okay? 68% of the population, let's say it's held within 160 to 180, then my standard deviation would be 10.
Is that because the curve's wider?
Yeah, the wider the curve, the larger the standard deviation. Cool? Really, really powerful, allowing us to predict where populations fall, allowing us to plan all that sort of stuff. So this is pretty powerful mathematics. I know it feels a bit baby, very much linked to the binomial distribution. What's some of the differences between the binomial distribution? Are we dealing with continuous or discrete data? Discrete. Does it have to be symmetrical? Does it have to follow a bell curve shape? It will likely follow a bell curve looking shape, but it won't be exactly like that symmetrical nice bell curve. Cool? And that's because the probability of the event determines how that looks. So they're the key differences. Be aware that we also need to learn our calculator skills, so I'll probably do a separate video right now for that, so get your calculators out.